Hello, this is the Gearbox design for a lawnmower. We are Team 10. That is Scott Lyon, Jonathan DeGroot, and myself, Elijah Meeman. Okay, so to begin with an introduction, just a brief history of gears. Gears can actually be traced back to 27 BC. The first use of gears is evident in the first watt wheels and mechanical clocks that were created in the time period between 723 and 725 AD. Since then, gears were widely used and implemented in the onset of the Industrial Revolution in the 1800s with inventions such as the automobile. Many modern-day machines use gears now and gearboxes as a means to transmit torque, and in regards to our project, we are analyzing it for a lawnmower. So the problem statement here is to design a gearbox capable of transmitting 6.5 horsepower. Our input speed is 2,050 rotations per minute. Our designed output speed is to be 200 RPM. It is to be used for medium to low precision applications with moderate shock in a high humidity environment. And our operational temperature is going to be room temperature plus or minus 50 degrees Fahrenheit.
So to begin the gear selection from the catalogs, we first had to come up with some preliminary calculations or estimates to go to the catalog with, and then follow the Boston Gear catalog procedure. So before we came to these final results, we started with finding the train value, which is dividing the the output RPM divided by the input. From there, we were able to find the diametral pitch, the estimate, and from there, we were able to mess around with different teeth counts to get the desired output of 200 RPMs. So in the end, we came up with the estimates of roughly 2.67 inches and 8.67 inches for the Gear 3, and then we went to the Boston Gear catalog, selected the gears that were the closest to the values that we had found, and again using the catalog procedure, which is the load and the service factor and the torque and horsepower requirements. So based on that, we selected 2 spur gears, 2 bevel gears, because we are trying to take the power from one axis to another at a 90-degree angle. And down here just shows the actual gear item numbers selected from the catalog. So once we selected the gears from the Boston Gear catalog, we had to analyze them to make sure that they would still stand up to the AGMA analysis and they wouldn't fail. It was also a good reference check to see if we had chosen the correct gears. So after running AGMA analysis for straight bevel gear and a spur gear, looking at the bending stress and the contact wear, we came up with these values. For Gear 2, it had a safety factor in the bending for 6.22, a wear of 1.37. Gear 3 also passed easily. The lowest safety factor seen was a 2.89. Gear 4 and Gear 5, which was the bevel system, was based off horsepower rating, and as you can see, our maximum horsepower was 6.5, and the minimum that it could handle, the maximum that it could handle was 6.65, so everything passed. After we selected the gears, we then went to the shaft design and the bearing selection. The shaft will go from 1 inch through the bearing, 1.25 inches through each gear. Each gear has the same bore diameter. This is just an intermittent diameter as the biggest point of each shaft, and then it steps back down, eventually going back to 1 inch through the bearing.
Okay, so for our cost analysis, we basically, after we found all the gears from our catalog, we found similar ones online and found prices for them. You can see it's a bit high, and that's mainly because this is just like a prototype. We're buying individual gears. If this is mass produced, the cost would go down a lot more. So this is just a SolidWorks drawing of our design. As you can see, our housing has a bit of an abnormal shape, but that's just to save on space, because if this is going to be used in application with an engine or something, you need as much space as possible for all the components. Basically what we did is we took our shafts, which you see here, and you can see the different diameters of the shafts. We put them in the orientation we needed in order to get our output RPM of 200 there and our input of 2,050 here. And then we kind of built the housing around it. And the housing is designed in a way so that all the bearings are mounted in the housing to make it as strong as possible. It's mounted into the actual frame of the housing so that we don't have just mounts hanging in the middle of the housing, which don't make it very structurally sound. So this was our design here, and as you can see, most of the bearings, all except one, can be mounted from the outside very easily and just pressed into these cavities. The one from the inside will have to be when it's separated. You mount the gears, and you can slide that bearing up in there and push it into place. Okay, and in conclusion, basically, We did our AGMA analysis on all of them, and we confirmed that they all worked based on all our calculations. The gearbox was designed according to gear selection and demonstrates the mates between gears. The structure design is specified and chosen to accommodate bearing mounts on both ends of the shaft, and mainly it was designed around those mounts, showing that they would be able to house the bearings very easily. And then we learned how to apply the gear catalog selection procedure, and we just compared all these to the AGMA to make sure that they work properly. Thank you.